And why would you do something like that in another sense? Well, if we are doing reasonably well in these calculations that were done without scattering, but we have scattering in the emitter, that's already incredibly important. But if we wanted to do scattering in the central device, we know that is a very hard thing to do. In non-equilibrium green functions, to do scattering is computationally incredibly expensive. So you want to reduce the domain in which you do scattering as much as possible to a domain that makes sense. So if we just wanted to do non-equilibrium inside the central device domain, we need to find ways to just look at the central device domain and not do scattering in this huge domain. And basically, if you do scattering calculations that typically scale in the order of n squared or n cubed, where n is the number of nodes in your system. So if you can make n significantly smaller, you will do that. And when I will show later scattering calculations where we've done these for realistic structures, that is what we've done. We've taken the contacts in, treat them in equilibrium, and then we do scattering in just the central domain, and we include phonons, interface roughness, etc. All right. So now let's compare these new boundary conditions to what was the state of the art in 1994. So typically, the choices you had were, you computed a bandage diagram and you scratch your head and said, I have no idea how to build that. The things I know how to do in quantum mechanics in these so-called quantum transmitting boundary conditions is to attach boundary conditions for flat bands. Because you can analytically know how these states scatter out, right, with scattering boundary conditions. So the two choices you pretty much had is you would attach a flat band way out on the left, or you might make a wild guess and sort of attach them somewhere closer to the central device. But those were the choices that were pretty much pursued. So let's see what happens if you do that. Well, in both choices, you get an IV curve that looks roughly N-shaped, right? It goes up, it goes down, and goes back up. Except the two give dramatically different results. And with the previous lectures that we had on this topic, you kind of understand why. Well, if you inject just from out here on the left, way out on the left in blue, only carriers that are sort of bubbling thermally above this barrier will make it through the structure. So that means if the central resonance in the central RTD comes over or at close to this bump, it's going to shut off because there's no coherent transmission through this channel anymore. So it's going to shut off early. And if you just attach these green flat lines right to the left and the right of the RTD, you know, you're completely omitting the details of this triangular well. So your source of electrons, in a sense, is too large. It's a huge source. And it's going to take a higher voltage to pull the resonance past this very deep bucket of electrons, so to speak. So the IV curve will turn off too late. In fact, if you put your experiment, this is now with a theory, which pretty much overlaps experiment as I've shown before, is you completely are unaware of these wiggles that are due to this coupling in the emitter, and your voltage is off on a logarithmic scale. What you have on the right is a log-log plot, right? This is exponential orders of magnitude that you can be off. Right? Your voltage is off by a factor of 20 ballpark, and your current is off by a factor of 20, depending on what boundary conditions you are. That is how far off the state of the art was at the time. All right, so now I made a big deal about these boundary conditions. Okay, so we are getting pretty close to the experimental data. We get the wiggles in the curves, and now you can say, well, Klimek, I mean, this is not even close, right? What's with the valley current? You made the point that we want to understand valley current, but you're not even getting close to the valley current. So let's try to understand that a little bit more. In the previous lectures, we also showed that it's important to look at charge self-consistency, right? So the previous simulations I had shown just the Thomas Fermi potential, and we've shown that charge self-consistency starts to linearize the IV a little bit, and it raises the peak up a little bit. If you include a contact resistance of 2.5 ohms, the whole IV also leans over a little bit, and the peak doesn't change, but you can basically overlap the experiment in terms of peak for this device. But you're still not getting the valley current right. So, valley current is due to scattering, right? That was the state-of-the-art knowledge. So we spent a lot of time putting scattering into NEMO1D. So let's look at that. Let's explore that. Okay? That's going to be in the next lecture. Do you guys understand roughly the boundary conditions? How they're important now in realistic devices? Because then we'll just move on.